Now that we've looked at the concept of confidence intervals and how our samples should produce results that are within what we expect the population parameter to be, we can now take this to the next step and see how we can actually perform hypothesis tests. And in this section, we're going to specifically look at two different approaches for hypothesis tests. The first one being the critical values approach, where we compare z-values, and the p-value approach, where we determine probability of our sample outcome. At first, let's just talk about hypothesis testing in general. Anyone can make claims about a population parameter. We see this all the time. We hear it in movies, we hear it in commercials, we hear it all the time. 4 out of 5 dentists prefer Starbright toothpaste to other brands. Fewer than 1% of dogs attack people unprovoked. In any given one period, 9.5% of the population, or about 18.8 million people, suffer from depressive illness. And the list goes on and on and on. Literally, if we watch television or listen to political speeches, we're hearing statistics being thrown at us all the time. And much of these statistics that we hear come from hypothesis testing. And in science, if you've ever taken a science class, you know what a hypothesis test is. We first put forth some sort of theory or premise that we want to test. And so a hypothesis is just that theory. In statistics, we actually, if we were going to do a test, we put forth two hypotheses, and both of these hypotheses are opposites of each other. The first one we call the null hypothesis, and the second one we call the alternative hypothesis. The null hypothesis is the current belief, the status quo about a population parameter. The alternative is the one that we wish to replace it with. So if we're putting forth an alternative hypothesis, we are usually in the research position, and we are believing something different about what is currently believed. Discerning between these two is very important before we go any further into hypothesis testing. So let's look at an example. The machinery at a chocolate factory has been overhauled, and the manager suspects that the chocolate bars produced are no longer falling within the 4-ounce average as they should. In this particular situation, the null hypothesis is that mu is equal to 4 ounces. The alternative we determine by the wording of the question. In this case, the direction of my alternative is really non-committal. If we look at the wording, it says the chocolate bars produced are no longer falling within the 4-ounce average weight as they should. So we know that what was happening before is that the chocolate bars are 4 ounces, but now we're either saying that they're less than 4 ounces, in which the manager would be concerned because then they could be committing fraud by saying that they're 4 ounces, and then secondly, they could be more than 4 ounces, which would also be a problem for them. So because of the wording of the question, the alternative hypothesis in this case is that simply they are not 4 ounces as they should be. This is what we are going to research and try to study. Basically, we want to see whether or not there's statistical evidence to prove that the chocolate bars are not falling within the 4-ounce average. In this study and in every study, we always assume the null hypothesis is correct unless our data disagree significantly. And so we assume that this holds to be true. And that assumption is really important because we're going to compare our results to this assumption. If we get results that differ significantly with that assumption, then we reject the null and assume the alternative is correct. Let's look at some other examples and see if we can come up with the null and the alternative hypothesis. So for example 2, it's generally accepted among educators that the average student studies no more than 15 hours per week. A national student organization claims that its members study more than the national average. Now in all of our hypotheses, the null is always an equals. And you're just going to assume that. So we want to look for the key measurement of which the null is equal to. And in this case, we're talking about a mean, an average of 15 hours per week, right? So our null is actually that mu is equal to 15. The alternative is the one we want to really pull from the wording of the question. In this case, it says a national student organization claims that its members study more than the national average. So our alternative is the one that we're going to try to prove is that mu is greater than 15 hours. And again, the null is always that mu is equal to 15 hours. Example 3. A leading news agency claims that the president's approval rating has dropped over the past 3 months. Previous polls put the president's approval rating at a minimum rate of 56%. The president's chief of staff wishes to test the claim since an election is approaching. See if you can look through the wording of the question to determine what the researcher wishes to prove in this study. Now in this case, we're talking about a percent. And so if you wish to think about this a little bit more, hit pause. Otherwise I'm going to proceed. So we have a percentage that we're measuring. In that case, we're trying to measure a population proportion, which is P. So in this case, the status quo, the current belief, is that 56% is about where the president's approval rating is. And the claim is that the president's approval rating has dropped, and this is the claim the chief of staff wishes to test. And so our alternative is that P is equal to 0.56. I'm sorry, that's the null. I think I said the alternative. The alternative is that it's less than 0.56. So sometimes we are going to be testing means, as we saw in the first one, and sometimes we're going to be testing proportions. We're testing proportions if we're talking about percentages, fractions, or decimal values. Example 4. Leading authorities have stated that approximately 1% of dogs attack people, even if the dogs are unprovoked. An animal rights organization believes that 1% is not accurate. Pause. In this case, we are not given a real direction. We know that this is, again, a proportion. We're talking about a percentage. But all we're told is that 1% is not accurate. That doesn't lead us in one direction or the other. Even if we think, because it's an animal rights organization, they might consider 1% to be too high. But the way the wording of the question is, it just says 1% is not accurate. That doesn't give us a direction. So our alternative hypothesis is that the proportion is not equal to 1%. So once we have established our hypotheses, we then want to decide which of the hypotheses the data supports. In understanding how to do this, we need to think of an analogy of the criminal justice system as it kind of plays in to how we perform these tests and how we approach the null and the alternative. Under the criminal justice system, we have a defendant and we have a plaintiff. The defendant is the one that's under attack, being prosecuted, and really whose life is about to be changed one way or the other. And the plaintiff is the one who is presenting the case against the defendant. Under the American justice system, we assume the defendant is innocent unless proven guilty, and the plaintiff is the one who has the burden of proving guilt beyond reasonable doubt. In a hypothesis situation, the defendant would be like the null hypothesis, and the alternative would be the plaintiff. We assume that the null hypothesis is true, and so we give it precedent over the alternative. The alternative would replace the null as the new current status quo, and so it needs to prove its case significantly. So this goes back to the idea that we are assuming the null is true unless the evidence goes the other way. So how do we perform the test? In a hypothesis situation, the evidence, of course, is given by our results from our study, which would be our sample from the population. We call the sample from our population the test statistic. If you recall, statistics come from samples, and parameters, numbers that are representing population values, are called population parameters. So, easy thing to remember, a test statistic comes from a sample. A parameter comes or is describing a population. We do not have a jury, of course, but the test statistic, the sample we take from a population, we would assume would produce values that are close to my population parameter. We saw this in the central limit theorem, that if we pull samples from populations that are large enough, and the larger they are, the more accurate we see that they become to the true population value. So if we pull a random sample from a population, we assume that its value, though not equal to the population value, should be close to the population value. If, for example, we flipped a coin 100 times and only 20 times did it come up heads, we might start wondering whether or not that coin was fair. Not because it's not possible to have 20 heads come up in 100 tosses. We've seen in probability how that can occur. However, it's just highly unlikely. And so we base our decisions on the likeliness of the outcomes that occur when we do our experiment. How much evidence do we need exactly? Well, in statistics we say the evidence is overwhelming if it is proven statistically significant, meaning there would be a highly unlikely occurrence of this if indeed the null hypothesis was true. And to get more specific about that, we want our results to be statistically significant if they exceed the bar of significance that we set. The bar of significance that we set is called the level of significance. That level of significance is akin to the idea of reasonable doubt. Our goal, of course, is to surpass the bar of reasonable doubt. In fact, the level of significance is directly related to the level of confidence. You can think of the level of significance as just the other side of the coin for your level of confidence. The measure of how confident we are that our population parameter lies within our confidence interval. That's our level of confidence. So we represent our confidence level with C. Alpha is how we label our level of significance. And in fact, the level of significance is simply 1 minus our confidence level. In other words, it's complement. We would expect most of our values, in this case, we have 1.96 and negative 1.96. We would expect 95% of the time that our samples should fall within this area, if indeed the null is located at the middle. Remember that we always used equal to for our null, and that's not by accident. Saying that the null or the mean is equal to something means that we believe this is where the true mean of the population lies. And the confidence level represents this body, and it represents what should happen 95% of the time. The level of significance is the area of our tails. It's the area of the place that we would not expect our sample to fall, if indeed the null was true and that our mean lied here at the middle. So let's talk about the conclusions. After the evidence is weighed, a conclusion, of course, must be drawn. And we draw them very specifically, just like in a court of law, a decision is drawn very specifically. We never say that a defendant is innocent. We say that a defendant is either guilty or not guilty. The reason why we don't say they're innocent is because that was never under question. We assumed their innocence from the beginning. And there are times where maybe someone really is guilty, but the evidence just does not surpass our bar of reasonable doubt. And so we go with the assumption that they are innocent. If the evidence is overwhelming, we say it's statistically significant. We reject the null hypothesis. Remember that the null hypothesis we assumed to be correct. So in rejecting it, we are saying that it is guilty or it is not correct, and we're going with the alternative in that case. If the evidence is not shown to be statistically significant, we do not say that we reject the alternative. We simply say that we fail to reject the null hypothesis. So, in terms of the null hypothesis, we either reject or we fail to reject. And then we say that the evidence seems to either support or not support the alternative. In terms of rejection, we always describe the null. We reject the null hypothesis, and if we reject the null, then we say the evidence supports the alternative. If we fail to reject the null, then we say the evidence does not, that there is insufficient evidence to support the alternative. In failing to reject the null, we are not concluding that the null is true. Instead, we're simply saying that the evidence is not compelling enough for us to reject it. Finding a defendant not guilty is not the same as finding him or her innocent. Again, we assumed innocence, and we assume the null is true. Unless we can see evidence against that fact, we fail to reject it. So here's an example. It's generally accepted among educators that the average student studies no more than 15 hours per week. In the spring newsletter, a national student organization claims its members study more per week than the national average. After performing a hypothesis test at the 95% level of confidence to evaluate the claim of this organization, the researcher's conclusion is to reject the null hypothesis. Do the researcher's findings support the organization's claims? So first thing we need to do is decide what is our null and alternative hypothesis here. We already know what the null is in terms of the symbols that we will use. However, we need to look at the wording in order to determine the alternative. In this particular problem, we are talking about an average. So again, 15 hours per week is my average. So that's my null hypothesis, that the average number of hours spent per week studying is 15 hours. The alternative we get by looking at the question. See if you can read through that one last time, hit pause, and decide which value, less than, greater than, or not equal to, is appropriate for our alternative hypothesis. And the alternative hypothesis is greater because it says the organization claims its members study more per week than the national average. So greater than is the appropriate symbol. The question then, if we have, if the researcher's conclusion is to reject the null hypotheses, do the researcher's findings support the organization's claims? The answer is yes. The null hypothesis would represent the idea that the organization's members are the same as the general population, that they also study on average 15 hours per week. Rejecting that, we're supporting the claim that the organization's members study more than 15 hours per week, or the alternative hypothesis. Here's another one. See if you can come up with the alternative and the null, and then ask yourself, do the findings support the counselor's claim? Hit pause. In this case, the null is that P, the population parameter, is 10%. And our counselor believes that it's less than that. He believes that that percentage is too high, so he believes that P is less than 10%. In terms of the counselor's claims, we failed to reject the null hypothesis, meaning we failed to reject the 10%. Since the results led to failing to reject the null, the data fails to give us enough evidence to reject the Board of Education's claim that about 10% of the percentage of high school sophomores considered dropping out of school. That doesn't mean that the board is correct. It just means that there wasn't enough evidence to reject it. So as you've seen, we basically have three different symbols that we use for the alternative hypothesis. The null hypothesis is where our equals goes, and then the alternative is either less than, greater than, or simply not equal to. These three different symbols that we can choose for the alternative hypothesis lead us to three different tests which are determined by our alternative hypothesis. If our alternative hypothesis has a less than value, we are performing a left-tailed test. If it's a greater than value, we're going to be performing a right-tailed test. If it's a not equal to value, we are performing a two-tailed test. The tails in this case represent the area of my significance level. And we also can call this area the rejection region. Now, if we are approaching a hypothesis test by looking at the regions that we call our rejection regions, we are doing a critical value approach, and this is the first approach that we're going to look at. Our conclusion rule for rejection regions is that we are going to reject the null hypothesis if our test statistic, which comes from our random sample, falls within the rejection region. The location of the rejection region depends on the type of test we're going, which depends on our alternative hypothesis. If we believed that the mean or the proportion was less than our stated null hypothesis, then we're performing a left-tailed test. And we're going to pick a significance level for that test. The significance level we choose will give us a boundary value that separates this rejection region, which is on the left, where we reject the null, if our test statistic falls over here, and our failing to reject region, which will be to the right of that. If the null hypothesis was true, we would assume our data should fall within this area, which has the higher percentage probability. And it's what we expect given the central limit theorem. Most samples taken from populations are going to fall fairly close to the mean. They may stray a little bit far, but they shouldn't go too far. If our test statistic is so extreme that it lands over here, meaning we get a z-value that's far beyond what we expected, then we begin to question whether or not the null really is true. So if the null is true, we'd expect the test statistic to fall into the non-rejection region. If it falls within the rejection region, we say it's extreme enough that we must reject the null hypothesis. In a right-tailed test, we have a critical value as well, which has a rejection region to its right. And of course, the area to its left would be the fail to reject region. Again, our alpha, our significance level, is equal to the tail area of our rejection region, where the non-rejection region has the area of our confidence. For a two-tailed test, we have two boundary values, so two critical values that represent two critical regions. Notice that for our alpha, for each of these tails, we have to divide it up by 2 evenly so that the area here, if we added them up, would equal to alpha. Failing to reject region has our confidence level, because this is where we're confident that if the null is true, our test statistics should fall between, or should fall within it. So, now when we're dealing with population proportions, and these are the first type of tests that we are going to run, the best estimate is a sample proportion, of course. If we want to know a percent of the population, we need to run, we need to get a sample and see what that sample tells me. Now, this is kind of some small print, we might say, on running tests with proportions. We have to have a sample that's big enough such that the n times the expected value of p is greater than 5, and n times the probability of failure, 1 minus p, is greater than or equal to 5. If these two conditions are met, then what this means is we are allowed to use a normal distribution table, and hence we can use the z-score. The z-value, which is how we're going to calculate the standard deviations of our test statistic, is given by this formula. P hat minus P. Notice that this is my sample number and this is my assumed population number. If we compare those two by subtracting them and then divide by the square root of P times 1 minus P, so P times its complement, and divided by n, we will get how many standard deviations our P hat value is from the middle. So let's run a full-on hypothesis test using a critical value approach for a proportion. So in a sample of 48, in a sample of 88 adults selected randomly from a town, it's found that 4 of them has been exposed to a particular strain of the flu. At the 0.01 significance level, test the claim that the proportion of all adults in the town that have been exposed to the strain of the flu differs from the nationwide percentage of 8%. So our first step is to establish our hypotheses. In this case, it is believed that the nationwide percent is 8%, and so therefore we expect this town to fall within or close to 8%. So status quo is that P is equal to 8%, but in this case we believe, or we're trying to check out whether this town differs from the nation in general. So the word differs is a key word here. It tells us that our alternative is not 8%. It doesn't commit us in one way or the other. Okay, secondly, we want to determine the critical values for this confidence significance level. In this case, we picked a 0.01 significance level. So that's a 99% confidence level. If we go to our tables and note that we have a two-tailed test, if we go to our t-table and look at the bottom, since we're doing a proportional measurement, we're going to use z, as we saw in the previous slide. And in fact, we're always going to be doing or using the z values with our p's. Those criteria, those small print items, those will always be satisfied for the problems we work. But if we look at the z value for a 99% level of confidence, we find that they are positive and negative 2.576. Two ways you can find this. You could use this, of course, using technology, just like we did before, keeping in mind that just like with confidence intervals, we've got two tails in our picture. The other way to do it is to look at your t-table. If you go down to the bottom, because we have a not equal to, this tells me we're doing a two-tailed test. So at the very bottom of the chart, we go over to two-sided p and find specifically 0.01. 0.01 split up into two tails means that we have 5% in, or point, I'm sorry, not 5%, but half of a percent, 0.5%, 0.005 in each tail. So these are set up ahead of time. We know exactly the bar we have to surpass with our critical values. We have to get something beyond negative 2.576 or something beyond. This should be positive 2.576. I don't know why that negative's there. So now we run our test. From our sample, we determined 4 out of 88 exposed to the flu in our town. And if we find that value of p hat, we find that it's about 4.55%, or 0.0455. We always want to use the decimal form of the numbers. So we find the difference of that from the assumed 8%, which matches the nationwide percentage, and then we divide by 0.08 times 0.92 over 88. If your calculator opens up a parenthesis when you open up a square root, then you need to just enter this straight in. Just go 0.08 times 0.92, its complement, divided by 0.88, and then close your parenthesis. Otherwise, you'll start to get layers and layers of parentheses, and it's very easy to get the wrong result with your calculator. Also, if you're entering it all at one time, of course, we want to put parentheses around the top difference there. So we get negative 1.195. This tells me how many standard deviations my test statistic falls from the mean. This is about right here. So because our test statistic fell within the area that we expected it to with a 99% level of confidence, this was not extreme enough for us to discount the null hypothesis. So in this case, we would fail to reject the null hypothesis. There is insufficient evidence to conclude that the proportion of adults exposed to the flu differs from the nationwide percentage. Notice a couple of things here, and you can use this as a template in drawing your conclusions. Whenever we talk about rejecting or failing to reject something, it should always be in terms of the null hypothesis. Fail to reject the null. If we fail to reject the null, we say there's insufficient evidence, and then we write out and write our conclusion based on what the alternative said. In this case, it said that they suspected it differed from the nationwide percentage. And so here we say there's insufficient evidence to conclude that the proportion of adults exposed to flu differs from the nationwide percentage. So after sufficient evidence to conclude, I'm simply restating the alternative hypothesis, which almost matches exactly with what was set up here. Let's look at doing this from a different approach, and this is called our p-value approach. Although the critical value method is something that we look at and we are going to use on some of our homework problems, it isn't necessarily the most commonly used method in research articles and journals. The p-value, in fact, is the value that is more often used. The p-value is the probability of obtaining a sample that we got, or something more extreme than what we got. And of course, the idea of more extreme changes on which type of hypothesis you're performing. But in general, the more extreme area will always be the area to the nearest tail. The definition of more extreme changes, if we're doing a left-tailed test, then we would go further to the left to see the area that would be more extreme than our test statistic. For a right-tailed test, it's going to be the area further to the right than our test statistic. And if it's a two-tailed test, it's the area further to the right or further to the left of our test statistic, depending on its position. So if we landed on the left, we're going to take that area. If we landed on the right, we're going to take that area. But then we're going to double it. And this is one of the tricky things about finding the p-value with a two-tailed test is we have to remember that the true value of our p-value is always the area to the left or the area to the right, depending on where it lands, and then we double it. So let's practice just finding a probability value. For a left-tailed test, we would calculate the p-value for a hypothesis test with the following hypotheses. Assuming the data has been collected and the test statistic value is negative 1.27. So assuming these hypotheses, 0.0 or 0.45 and 45, we're assuming we're talking about a percentage, so we have p there. Notice our alternative is a less than symbol, and so we know we're doing a left-tailed test. Negative 1.27 was the result of my sample. And so the p-value is going to be, since we're doing a left-tailed test, the area to the left of negative 1.27. See if you can find in the normal curve the area to the left of negative 1.27. Of course, in this case, we would use normal CDF because we're using a normal curve, and we would find the area to the left of the z-value of negative 1.27. Pause. The area to the left of negative 1.27 is 0.1020. Okay. Again, the idea with any test is that we assume that the value should land close to the middle. If it doesn't, then we look at the area to the left of where it fell. Now, the chance that it would fall over here by accident, meaning that the null really is here, but our particular sample just happened to fall way far away. Well, the probability that would fall where it did or somewhere more extreme to the left of it is equal to 10%. So we would look at this from a probability standpoint. We would say there's a 10.2% probability that a value like the one we got or something more extreme would be selected if the null was true. In other words, we're almost looking at the probability of the null being true. Because if the null was true, we wouldn't expect to fall as far away from it as we did. Now, even though 10% is a low probability for something being true, and if we're basing this on the null's truthfulness, that would seem like a lot of evidence. But in a lot of cases, we would fail to reject the null hypothesis. We're not really getting specific here about our decisions yet. We'll get to that here in a minute. We're just looking at how to find the p-value. In a right-tailed test, here's our hypotheses and our z-value that we got from our test statistic, which is our sample from the population. That value turned into a z-value of 2.21. So 2.21 is on the right, and so because we're also doing a right-tailed test, the p-value will be the area to the right of 2.21. Using your calculators, see if you can calculate the p-value for this problem. Using normal CDF, 2.21, comma something more extreme, comma 0, comma 1, gives us a p-value of 0.0136. Therefore, for this problem, we would say there's about a 1.3% probability that if indeed the null was true, that it is located right about here, that we would land where we did or possibly further to the right. There's about a 1% chance that that could happen. This again provides evidence against the null being true. In fact, the lower the probability, the more evidence we have that the null is lying when it says that the mean or the proportion is in this area. Two-tailed test. Calculate the p-value for a hypothesis test with the following hypotheses. Assume the data has been collected and the test statistic was calculated to be negative 1.99. So in this case, we have a two-tailed test because our alternative is not equal to 9.1. These are just random numbers that I'm picking for this problem. So negative 1.99, of course, is the result of my sample, and it landed on the left. The p-value then, to find the p-value, we would first want to look at the area to the left of negative 1.99, which would represent the more extreme area beyond our test statistic. The area to the left of negative 1.99 is 0.0233. Verify that with your calculators. Now, even though that is the area to the left of the test statistic we found, because this is a two-tailed test, that is not my probability. 0.0233 is not my p-value. We also have to take into account the area to the right of positive 1.99. And the reason why we have to do that is because this is a two-tailed test. So with a two-tailed test, we always have to have two extreme areas, one to the left of the test value we found, and then the other on the opposite side. Well, the area on the opposite side is going to be the same as the area on the left. So if we take the area we found and we multiply it by 2, we get 0.0466. This is my p-value of this problem, 0.0466. And so therefore what we say is that there is a 4.66% probability that a value more extreme would be selected if indeed the null hypothesis was true. Grab your calculators. Let's run a couple more tests. So calculate the p-values for the following hypotheses. We have mu equal to 66. Our alternative is that the mu is greater than 66, and my z test statistic value is 2.12. Find the p-value for this problem. This would be a right-tailed test. Sorry for that, it's a typo right there. Because it's a greater than symbol, we are running a right-tailed test. And so the area to the right of 2.12 is 0.0170. Here's our next one. Determine what type of test and what the p-value is for this problem. Because we have a not equal to symbol here, then we are running a two-tailed test, and so we find the area to the left of negative 1.56, and that area is 0.1188. And for the last one, here are your hypotheses, and here's your test statistic. What type of test and what is the p-value? In this case, this is a right-tailed test because we have a greater than symbol. And our test statistic value is 3.21, and the area to its right is 0.0007. So that means the p-value has a value of 7/100ths of a percent. Now, we've talked about how the lower the p-value is, the more evidence we have against the null. So in discerning whether or not we are going to reject or fail to reject, we need to set some sort of decision criterion. And here's how we do it. We compare it to the chosen level of significance alpha for the problem, and the choice is very clear. If our p-value comes out less than or equal to alpha, then we are going to reject the null hypothesis. If the p-value is greater than alpha, then we are going to fail to reject the null hypothesis. In other words, if the probability of a more extreme value is smaller than our significance level, we assume the null hypothesis is false and we reject it. If the probability is greater than our significance level, then we say we fail to reject. So, for a given hypothesis, the p-value is calculated to be 0.0123. Now, if our stated significance level is 0.05, what is the conclusion of the hypothesis test? In this case, Since it's less than 5%, we would conclude that the evidence supports rejecting the null in favor of the alternative. What if the confidence level for the test was 99%? What would be my conclusion? If we set the confidence level at 99%, that means we have a significance level of 0.01. Your significance and your confidence should always be complements. And 0.0123, though low, is still greater than 1%. And therefore, we would conclude that the evidence is not compelling enough, and that we would fail to reject the null hypothesis. A p-value approach in doing a hypothesis is as follows. And they're very similar to a critical value, but there's some definite differences. The first thing we're going to do is state the null and alternative hypothesis. Second, we're going to set up the hypothesis by choosing and stating the level of significance. We want to decide the level of significance ahead of time so that we're not just moving the bar so that we get the results that we want. Thirdly, we go and we gather our data and we calculate the test statistic. Notice that we're not concerned about the critical values or rejection regions when we're doing a p-value approach. We simply look at two numbers, the test statistic and its corresponding area, which is our p-value. We then compare the p-value to the significance level we chose, and we draw a conclusion based on the above comparison. Remember that we always state our conclusion in terms of rejecting or failing to reject the null, and then whether the evidence supports or doesn't support the alternative. So here's our example. A local high school board has been advertising that at least 65% of the voters favor a tax increase to pay for a new school. A local politician believes that less than 65% of his constituents favor the tax increase. To test his claim, he has 50 constituents and 27 said they favored the increase. If the politician wishes to be 95% confident, does the information support his claim? In this case, again, we're dealing with a proportion. The believed proportion of the population is that 65% or 0.65 favor the tax increase. The local politician believes it's less than this, so our alternative is that P is less than 0.65. Now in this test, we see that we are allowed to use the Z because N times P is equal to 32.5, which is greater than 5, and N times 1 minus P is also greater than 5. Again, this is something you don't really have to worry about for our purposes. But what this tells us is that we can use a normal curve. Now, for our p hat value, we found that 27 of 50 favored the increase. Calculating the p hat value of that comes out to be exactly 0.54 or 54%. Now in your calculators and when you're finding the z, you don't always have to change it to a decimal. In fact, as you're plugging it into the z formula to find out the value of the test statistic on the z curve, you can just put 27 over 50 here minus 0.65. Your calculator will figure it out for you. Do remember, however, to put parentheses around that difference on the top. And also, if you're radical, your square root opens up a parenthesis when you open it up, that you just type in your results. Don't try to put parentheses in there. And then when you're done with all the numbers, close that parenthesis. This actually should be 1 minus 0.65, which would be 0.35. The result of this should be 0.35. And our result in this is negative 1.65, or if you, it may be a little bit different than that, depending on the numbers. So we did fall to the left just as we expected. Our 54% of course is less than 65%. The question then is this a significant difference for us to reasonably conclude that less than 65% of his constituents favored the increase? The p-value is the area to the left of negative 1.63, and if we use normal CDF to look that up, we find that the p-value is 0.0516. Compare this to my significance level. We want it to be 95% confident, and therefore our significance level is 5%. 0.0516 is just slightly greater than 5%. And so we fail to reject the null hypothesis. We would say there's insufficient evidence at the 0.05 significance level to conclude that less than 65% of this politician's constituents favor the increase. This is an example of how to do a hypothesis test for population proportions using the p-value approach. There are many more examples that you can look through. This concludes our portion of this lecture, but if you would like some more details and some more examples to look over the PowerPoint presentation that says Module 12. And as you scroll through that, and there should be a video as well that goes with it, you can have some more examples of how to perform these using a critical value approach and using a p-value approach.